All right, let's talk about C pointers. Man, they are something else. In the world of C programming, pointers are this incredible double-edged sword. Get them right, and you have this unbelievable power, this fine-tuned control over your computer's memory. But get it wrong, even by a little bit, and bam, your whole program can just collapse. So the big question is, how to use this incredible tool without, shooting yourself in the foot. So it all boils down to this, really. Are your pointers working for you, or are they working against you? Are they an asset or a huge liability? Well, here's a little secret for you. The key is to stop thinking about them as just variables. Instead, think of them as characters, each with its own personality. You've got your trusted allies, and then you've got the ones that are basically trying to sabotage your code from the inside. So come on, let's meet the cast of characters and figure out who's who. Okay, first up, the helpful pointers, your toolkit. All right, let's kick things off with the good guys, the heroes of our story. These are the pointers you absolutely want in your programming toolkit. They're the ones that make your code flexible and, most importantly, safe. And we're going to start with the most versatile one of the bunch. So meet the void pointer, or as I like to call it, the generalist. Seriously, think of this thing as a master key for your data. It's a special kind of pointer that doesn't care what data type it's pointing to. It can hold the address of an integer, a float, a character, you name it, it can point to it. And it's that awesome flexibility that makes it such a go-to tool for so many of us. But the generalist comes with some really important rules of engagement. For instance, when you use a function like malloc to get some memory, it hands you back a void pointer. But here's the catch, and this is a big one. Before you can actually use the data it's pointing at, dereference it, you absolutely have to tell the compiler what kind of data it is. That's called typecasting. If you don't, the compiler just throws its hands up. It has no idea how to read that memory, so it won't let you get the value, and you can forget about doing any kind of pointer math on it. Okay, next up in our toolkit is another hero, the null pointer, our safeguard. And this is so important. A null pointer isn't a mistake. It's not an accident. It's a pointer that we have intentionally set to point to, well, nothing. It's the universal sign in C programming that says, hey, this pointer is empty. Don't even think about using it. Honestly, it's probably the single most important safety feature you've got. Now, it is absolutely critical that you don't mix these two up. They sound similar, but they're totally different things. A void pointer is a type. It's a kind of box that's designed to hold the address of anything. A null pointer, on the other hand, is a value. It's what you put in the box to show that it's empty right now. So one's about what it could hold, and the other's about what it's holding right now, which is nothing. All right, section 2, the dangerous duo, the pointers that are out to break your code. Okay, we've met the heroes. Now, it's time to meet the villains. These are the pointers that are responsible for all those headaches, those mysterious bugs, those spectacular program-ending crashes. Let's pull back the curtain on this dangerous duo. First up, we have the dangling pointer. We're calling this one the ghost, and that's exactly what it is. It's a pointer that haunts a piece of memory that's not even there anymore. The analogy is perfect. Imagine you've got a key to a house. Then the house gets completely demolished. You still have the key, right? And it still looks like a key. But what does it open? A door to a pile of rubble? A hazardous waste site? That's a dangling pointer. It's a valid-looking address pointing to memory that's been freed and could now be anything. So how does this ghost even get created? It's actually a super simple 4-step trap that's so easy to fall into. Step 1, you allocate some memory. Step 2, you use it. Step 3, you do the right thing, or so you think, and you free that memory. But here is the critical mistake. Calling free gets rid of the memory, sure, but it does absolutely nothing to your pointer variable. Nothing. The pointer itself is still sitting there holding that old address, just dangling in the wind, pointing to who knows what. Okay, so if a dangling pointer is a ghost haunting a specific, known but invalid spot, then our next villain, the wild pointer, is a total menace, a loose cannon. This is what you get when you declare a pointer but you never ever initialize it. You haven't given it a real address to point to, and you haven't set it to null. So it's just pointing, somewhere, anywhere. And somewhere is the terrifying part. Because it was never initialized, it holds a totally random garbage address from whatever was left over in that bit of memory. It's pointing to some arbitrary spot in your program's world. Trying to use this pointer, it's like spinning around with a blindfold on and just firing a weapon. You might get lucky and hit nothing, Or you could overwrite some absolutely critical piece of data, causing this silent, insidious bug that you won't find for weeks. Or you just get an immediate catastrophic crash. It's pure chaos. Okay, part 3, taming your pointers. Let's talk best practices for safe code. All right, we've met the heroes, we've met the villains. The big question, of course, is how do we use the good guys effectively while making sure the bad guys stay locked up where they can't hurt us? Well, it all comes down to a few simple, but let me be clear, absolutely non-negotiable best practices. Think of these 4 rules as your shield against all that pointer chaos. Rule number 1, always initialize your pointers the moment you declare them. If you don't have a real address for it yet, fine, just set it to null. Boom. Just like that, the wild pointer menace is gone. It can't even be born. Rule 2, the second you call free on a pointer, immediately, in the very next line, set that pointer to null. This one simple step completely exercises the ghost. No more dangling pointers. The last 2 are just about using your tools like a pro. Always, always check if a pointer is null before you dare to dereference it, and always remember to typecast a void pointer to tell the compiler what it's looking at. It's really just simple discipline, but the payoff in stability is massive. So, at the end of the day, it all comes back to this idea. Stop thinking of pointers as just faceless variables. They have these distinct personalities, right? You've got the generalist, the void pointer that can be anything. You've got the safeguard, the null pointer that keeps you safe. And then you've got the ghost, the dangling pointer, and the menace, that wild pointer. Really understanding who they are, how to use the good ones, and how to defend against the bad ones, that is the real secret. That's what it takes to truly master memory management in C. So, with this new perspective, I'm going to leave you with a little challenge. Go look at your own code. I want you to think, which pointer bug are you going to hunt down first? Is there a menace lurking in there? A wild, uninitialized pointer you forgot about? Or maybe there's a ghost dangling around after a free call? Go take a look. I bet you'll find something. Thanks so much for joining me on this one.